This is a video going through some key things on section 2.2. The first thing I want to look at is finding inverses of piecewise functions that are invertible. So if we look at number 2, the first thing we're going to do is graph this piecewise function. So let's do that. If we plug in, remember how you graph piecewise functions, always start with the restriction. So if I plug in, for the top, if I plug in 4, for x, I'm going to get an output of 1, and I'm going to fill that in because it is defined for 4. And let's do one more point, given it's a line. If I plug in something like 6, I will get 0. Okay, so that top piece looks like that. And then for the bottom piece, I'm going to plug in the restriction again, which is 4. And normally I'd put an open circle, but its output is 1, which it's already filled in by the other function. So when I put in 4 to the second, I'm getting 1 again. So right on top of that already filled in circle. And then I like to sometimes, if it's in the interval, plug in 0 to get the y-intercept. So when I plug in 0, I get 9. Okay, so here's my graph. And let's first then answer the questions. Find the domain. All x values that are covered are everything. And same with the range. Now, is it invertible? Yes, it passes the horizontal line test. It's a one-to-one function. Every x value goes to a unique y value. So now I have to find the inverse. And finding the inverse in some ways is very similar to finding an inverse of non-piecewise functions. For each piece, I'm just going to invert it. So I'll start with the top piece. And so undoing this would be subtract 3, and instead of dividing by -2, I'm going to multiply. And the restriction part is the hard part. So let me just undo the second piece, and then we'll talk about the restriction. So x minus 9 over -2. Okay, so now remember what an inverse is and what happens with an inverse. The domain and range switch. So the new piecewise functions are such that you're on a different piece depending on where you are in the domain. So I need to know the different domain restrictions for each piece. So, and because domain and range flip, the domain restriction for the inverse will be the range of the original. So if we remember back to the first piece when we graphed it, this here was the first piece. So that has a range of y less than or equal to 1. So my domain restriction for the inverse will be x less than or equal to 1. And then the same is true if we think about the second piece. When we drew the second piece, it was this one. So we will say the range restriction would have been the range would have been y greater than 1, which means my domain restriction is x greater than 1. So domain and range flip. So to find the restriction for each piece of the piecewise function, you look to the range of the original. That's why graphing it really helps. Okay, so that was one aspect of what was talked about for 2.2. And now let's transition to talking about absolute value. Okay, so let's do number 9 here together. So number 9 is a function that contains multiple absolute values, and I want to rewrite it as a piecewise function without absolute values. Then I'm going to sketch it and state the domain and range. So first thing we do with this type of problem is finding the turning points. And the turning points are always where inside the absolute value equals 0. We're trying to figure out where inside the absolute value will change sign. So it looks like I've got 2 turning points, one at 1 and the other one is at -5/2. Now, in order to figure out how many pieces you are and what will constrain those pieces, put on a number line the turning points. So just make sure you put smallest to greatest. So I've got -5/2 and 1. So that means I'm really dealing with, there's 3 scenarios, 3 cases or 3 pieces you can think about. So let's go piece by piece. And so let's start with x being less than -5/2. Okay, so you literally are thinking, when doing this, if I plug in a value, because you want to write this without absolute values. So you're thinking about, for the absolute value parts, plugging in a value less than -5/2 to determine if it makes the quantity inside the absolute value positive or negative. So pick an easy number, less than -5/2, like -3. And so and the point is to rewrite this function without any absolute values. So I've got y equals, so 2x isn't in an absolute value, so that's always just 2x. But if I plug in -3 to x minus 1, that would make that quantity negative. And an absolute value, if it's negative, makes it positive. So I'm going to multiply everything inside that absolute value by -1. So that means I'm going to write it as -x plus 1. Okay, then I've got minus. Now let's think of 2x plus 5. Again, plugging in -3 to inside that absolute value. Well, that would result in inside being negative. So I've got to multiply everything inside also by a -1. Okay, so cleaning this up, this is y equals 2x minus x is just x plus 1. And let's distribute the negative, plus 2x plus 5. So this first piece will be 3x plus 6. So now we're done with the first piece of the piecewise function. Okay, let's do piece 2. Piece 2. So no, I didn't include equality for -5/2, so let's include it here. So x greater than or equal to -5/2. And then I'll do less than 1. And okay, so think of a value that we're going to plug in for x in the absolute values. That's easy in this interval, and I would say 0. So that's what we're going to keep in mind. So let's rewrite y equals 2x just stays the same. If I plug in 0 for x minus 1, well, that makes it still negative, so I got to multiply it by -1. If I plug in 0 for 2x plus 5, well, now that makes that positive. So the absolute value is really just acting as parentheses. So it's just going to be minus parentheses 2x plus 5. So cleaning this up, we've got y equals x plus 1 minus 2x minus 5, which is -x minus 4. Okay, great. Piece 2 is all done. Third one is for x. I didn't put equality with the one in the second one, so I'll put it with the one here. Doesn't really matter, as I said in class, where you put equality. Just make sure you put it in one spot, because every point in the domain should have an equation it goes to, and only one. So I didn't include 1 in number 2, but therefore I'm gonna include it in number 3. Okay, so greater than or equal to 1. Again, y equals 2x isn't changing that part. If I think of plugging in something like 2, that would make x minus 1 positive, so we're not changing that at all. And it would still make the 2x plus 5 positive. So again, same deal there. It's just staying as 2x plus 5. So distributing, we get 3x minus 1 minus 2x minus 5. Or in other words, this will equal x minus 6. Okay. Now, remember what I said when you're graphing these types of functions, they should all connect. So before we do that, try to graph it. Let's just rewrite this in proper form. Piecewise notation would be, the first one is 3x plus 6 for x less than -5/2. Second piece is -x minus 4, and that's for x greater than or equal to -5/2 less than 1. Last piece will be x minus 6, and that will be for x greater than or equal to 1. Okay, so doing this graph now, I'm just going to bleed into down below here. Just a rough sketch, enough to get the shape of the graph and then be able to tell the domain and range. Okay, so I'm going to start at -2.5 or -5/2. And when I plug that in for x, it'll be -15/2 plus 6, which is just 12/2. So that's going to be -3/2. Okay, so we've got -2.5 the output's going to be -1.5. All right, and what was the slope of that? Oh, it was a positive slope. Again, we're just doing a rough sketch, so something that's going in this direction. So I'm going to say and I like to label the point. So this would be -5/2, comma, -3/2. Oh, and I really should do an open circle and then hope it gets filled in by the next one. Okay, so putting -5/2 in for the second piece would be +5/2 minus 4, which in other words, -8/2, which indeed is going to be -3/2. Perfect. And then when I plug in x being 1, which is the other extreme, I get -5. Okay, and right now it's an open circle. Oh, and also the y-intercept of that is -4. So I'm just going to go like this here. Okay, so far great. Everything's connecting. Okay, so remember when I plugged in 1, I got -5 for the output in the second equation. When I plug in 1 to the third, I get -5, which is going to fill that right in. And then it has a slope of 1, so it goes positive. If you want, you can plug in another point like 2, and you get -4 if you want a second point. So it looks like this. So there's your graph, and remember this was 1, -5. So I would say the domain, all the x values that are covered in number 9 are everything. And the range is also actually going to be everything here. So because this arrow here is going down and we got the other arrow going up. Okay, so that is writing a piecewise function, writing an absolute value function as a piecewise function, graphing it, and finding the domain and range. All right, let's now transition to the last part, which would be, here's an equation with absolute values, solve it. Okay, which one are we going to do? Let's do 12. All right, so we've got here multiple turning points. I've got 5/3, I've got -9/2, and I've got 8. So I'm going to put those on a number line. So -9/2, 5/3, and 8. Yikes, so that means I'm going to do, 4 different equations here. Okay. And so let's do equation 1. So if I'm plugging in the value into this equation, that's less than -9/2. So let's do -5. That'll make the first absolute value quantity negative. So I'm going to multiply by -1. Minus, it will also make the second negative. So -2x minus 9. And it will make the third negative, so plus -x plus 8 equals 16. All right, let's simplify this. -3x plus 5 plus 2x plus 9 plus -x plus 8 equals 16. So the left side, it looks like I have got -4x plus 2x. Is -2x, and then I've got 17 plus 5, so plus 23 equals 16, or -2x equals -7, or x is 7/2. And so the question is, I should have written, always write what that restriction is, less than -9/2, because that's important. So 7/2 certainly is not in that restriction of less than 9/2. So there is no solution from that piece. Okay, let's do the case 2. So case 2, we're going to say if x is greater than or equal to 9/2 and less than 5/3. All right, so that means this first quantity is still negative, so I multiply by -1. But now that we're greater than or equal to negative 9 halves, the 2x plus 9 would be positive inside, so I'm just going to treat the absolute value as parentheses. And then x minus 8 would still be negative, so minus x plus 8 equals 16. So solving this, we've got, let's see, negative 3, negative 6x, and then 5 minus 9 plus 8. So negative 4 plus 8 will be plus 4 equals 16, or negative 6x equals 12. X is negative 2. And is that in the restriction between negative 9 halves and 5/3? You bet it is. So that actually is going to be a solution. All right, halfway there. Third case is x greater than or equal to 5/3, and then we'll do less than 8. So 3x, so if I think of a value like 2, 3x minus 5 will be positive. Same with the 2x plus 9. So right now the absolute value is just acting as parentheses. And then the x minus 8 will still be negative. So minus x plus 8 equals 16. Once again, just combining like terms, we'll get, it looks like all the x's on the left are going to cancel because I've got 3x minus 2x minus x, so no x's left. And I've got minus 14 plus 8, so minus 6 equals 16, which is totally false. So there's no solution from that case 3. Final case is if x is greater than or equal to 8. All right, so in this case, it looks like everything inside the absolute value would be positive. So absolute value really is just acting as parentheses for all the cases. So let's see what we've got. We've got ended up with 2x. So minus 14 minus 8, so minus 22 equals 16, or in other words, 2x equals 38, or x is 19, which indeed is within the restriction. So there was 2 solutions from here. The 2 solutions were negative 2 and 19. Okay, so that was the second type of problem.